pictures up. If you don't remember, which definitely happens, you can only memorize so many things. The picture will clarify. Okay? Okay, give me the conclusion of that first one I gave you mostly. On a decreasing function. If you have a decreasing function, then there'll be the left side is greater than the right side, so you'll get overestimate. Decreasing function. I like it. Okay? What's another case of overestimate?
Left trapezoid.
Left trapezoid? There's no such thing as a left trapezoid. What are you talking about? All right, you mean a right-hand rectangle? Okay. Right-hand rectangle on an increasing function. Okay? In which case the right side, because it's increasing, the right side will be more than the left side, so you get more than you should be getting. Okay? What's the second estimation method besides rectangle? Trapezoids. You'll notice midpoints don't show up in here. You don't really go to midpoints increasing or decreasing, because if you have a midpoint rectangle, that kind of depends on the relative area. You just don't. There's no one hard rule of thumb for midpoint. So there is an estimation over there. But trapezoids, yeah. Overestimate. In what case do trapezoids overestimate? Yeah, when there's concavity, the trapezoid between the endpoints will be over if it's concave up. So trapezoids combined with concave up function. Okay? Something along those lines. You with me? Okay, so today's lesson is a good one. We've done a lot of tests, and some are more valuable than others. This is the best test there. The limit comparison test is the best test. It's super duper handy, and it smokes the direct comparison test. Why does that refuse to be on? Okay, here we go. The thought process behind it, I'll show you the formal test in a second, but the thought process goes something like this. Say you had one series over here, and this series over here, all the terms of it were exactly twice as big as the starting series, yeah? Now, if I knew that this first one converged, what would that tell you about this one? If all the terms of this one are twice as big, will it get infinitely large, or will it just be twice as big a sum as this one? Twice as big a sum as this one. So you could imply then that if there's a scale factor or a ratio between the terms, if this one converges, then this one must converge too, right? Twice as big as finite is still finite, right? Likewise, if this one diverged, then twice as big as diverging would be divergent. That's the idea behind the limit comparison test. If there's a factor between the two, or a proportion between the two, then they really have to behave the same way. You can't have double finite being infinite. Double finite is still finite. That's the idea. It's a comparison test, which I'll get to in a second, but it goes like this. You're going to be given a question series, does this converge or not? And like the direct comparison test, you'll find one that's like it, maybe a little different because of the constants in there or the coefficients, but like it, general in power, right? You then, instead of the direct comparison test where you try to prove one is less than the other like we have before, instead you take the ratio of their terms. You compare the terms. What are the terms like? Are they twice as big, 3 times as big, half as big, whatever? You compare the terms and you find that limit. Now, depending on how the limit comes out, you might be golden. If the limit is finite times 2, for example, if the limit is 2, then that would imply that the terms are approaching twice as big. And then there's a direct comparison between the two. If the limit was 5 times as big, 7 times, it wouldn't even matter what the number is. As long as it was some finite number, you know they had some kind of scale factor comparison between them, right? You could therefore then conclude that they have to converge or diverge in the same way. This one you're asking about it's twice as big as the one I know about, so it has to converge or diverge exactly like the one I know about. So if you get a limit that's between 0 and infinity, that means the terms compare favorably in a finite way, and I can conclude. If, however, the limit is 0, well, if the limit goes to 0, that probably means that the bottom was much faster growing than the top, and there probably wasn't a good comparison there. And so I can't really say they behave the same way. I don't know what that means. If the limit goes infinity, that probably means the top was much bigger. And again, there's not really a good comparison between the terms. I don't know how they relate to each other. Those would be inconclusive. That's the idea behind the limit comparison. All right? Now, just in terms of, bear with me again, I know you want to just get to the problems, but some of the ideas here. This test works well when you're looking at a series that's like one we know about, but maybe with a little extra monkey business, like a +5 or something that keeps it from being a p-series. Kind of like we did when direct comparison tests were used, right? All right. The beauty of this is it smokes the direct comparison test because the direct comparison test failed half the time. It was inconclusive half the time, depending on if it was plus when it needed to be or minus when it needed to be, right? The limit comparison test doesn't have that half failure rate. It will always work. It doesn't matter if it's +2 or -2. It works either way. So it's the first comparison test. It's the better comparison test. It fails, like I said, when the terms don't compare well. If you try this comparison test and get 0 for a limit, then that means one of either two things. The test just isn't right for the situation, or you chose a bad series to compare to. The terms don't really compare to each other. The series you're trying to compare to is not really like the one that they're asking for. All right? In that case, then, you either go at it a different way or use a different test. All right? So let's try the ones off the homework. You should have 8, 10, and 12 still. Now, I don't care. If you use these notes, then this is my preference. Would you do 8, 10, and 12 here, and then just put an X through the problem set boxes? If you're not taking these notes, then you might as well just put them in the problem set boxes. But just do them in one of the two places. Are you with me? Okay. So then, 8, 10, and 12. I'll put them up here as well, sorry. 8 is the series this. Now, we'll get to, just bear with me for a second. Had I done this by the direct comparison test, I think you know that n plus 1 is greater than n, so 1 over n plus 1 is less than 1 over n. And so the series, that's a summation, sorry. What do you know about the harmonic? It diverges. What could we conclude here? Ours is less than infinite. Could it be infinite still and just slower? Yeah, but could it also be finite? So you can see the direct comparison test is just a no-go here. It doesn't get you. It's inconclusive. The limit comparison test will work. So the idea is you first decide what to compare to. In this case, it looks just like a harmonic series. So that's what we're going to compare it to. You set up the limit. Now, it doesn't actually matter which one you put on top. The answer would either be 2 or 1/2, but it's either way, it's going to be finite either way. You know what I'm saying? So that doesn't matter. Don't sweat which you put on top. I'm just in the habit of putting the new one on top, but that doesn't have to be the case. So I'm going to compare 1 over n plus 1 over 1 over n. Now, you might have noticed that I'm throwing absolute value on here. There's this other aspect to these series that we haven't even talked about, and that is when you have either a negative term series or an alternating series. Alternating series tend to be a little more complicated, but the limit comparison test works for all, alternating or not. So get in the habit, please, of using absolute value. That way you won't have to relearn it and do that later. Absolute value will cancel out any negative monkey business. What's the limit of that? It is 1. I don't really particularly care if you show that step to clean up or if you could just mentally imagine that going to 1. Now that doesn't mean that the sum goes to 1 or the terms go to 1. It means that the ratio of their terms is pretty much 1 to 1, which you can kind of see how that would be going. I mean, if you thought way down the line, you're really comparing, say you looked at the millionth term, you're comparing 1 over 1,000,001 to 1 over 1,000,000. There's pretty much a 1-to-1 correspondence between the terms, right? And because there's a 1-to-1 correspondence between the terms, these series are going to behave exactly alike. So this series must obviously diverge because it's just like harmonic, which diverges. So now the conclusion looks like this. And this is, to me, what good calculus looks like. It's pretty common to college textbooks. The AP, you don't really do this piece of the work in an AP, so don't sweat that. It goes something like this. You'd say because, actually, I'm going to call this L so people know what I'm talking about. So because the limit, actually I guess I could say the limit is between 0 and infinity, both series or both converge or both diverge. That is to say, because there's a 1-to-1 correspondence, they behave just like each other. Either both converge or both diverge. Well, the series 1 over n diverges. Now you must say why. Why do you say that? It's P-series or harmonic, whichever you prefer, harmonic or P-series justification. So the series 1 over n plus 1 must diverge also. That's what the conclusion needs to look like. If you give me just diverges circled, you're going to really tick me off. It's a sentence or two. Understood? Okay. Try one on your own, like 8. What was that? Sorry, 10. 10, the limit as n, sorry, darn it, the series, and starting at 1 to infinity, 2n plus 1 over n plus 1 20 squared. Now this the limit comparison test is where it's at. It's so much better than the limit comparison test. So you'll see, what are you thinking? Just before you go off on the wrong track, what are you thinking maybe in comparison? 1 over, no, that's a bad choice. Try again.
1 over n squared. 2 over n squared. 2n over n squared.
2n over n squared.
2 over n squared. Okay, I was just thinking actually just that myself. Whatever. Okay, we can throw all that extra stuff in there too if you want. My point, sorry, this is new. I don't mean to mock you, but that's fun to mock you. The beauty of it is you don't even need to sweat all that direct comparison test. It's all gone. This will be a finite limit. 2 over n. That'll be a finite limit. It'll be different limits, but it'll still be finite. You know, they'll come out different, but the conclusion is that it's a finite limit and there's a comparison between the two. So it doesn't really even matter, but you definitely want to focus on the terms. This is n over n squared simplified. And all of the constants and coefficients, they're really a non-issue, you'll see. Just focus on the n behavior or the greatest powers. You with me? Okay. Okay. Right. Where's your conclusion mean? Something like, depending on if you used 1 over n or 2 over n, your limit might come out differently. If you used 1 over n, your limit should come out 2, yeah? What if you use 2 over n? What's your limit? It would be 1. Okay, so either way, it's fine. The conclusion will read the same because the limit, which is 2, is between 0 and infinity, which is to say they didn't totally behave differently, one totally outpacing the other. Both converge or both diverge. All right, so that's a start. Great. So they have to behave the same way. Now what do I do?
Say what the one figuring.
Yeah, you say what the one you know about does. 1 over n does what? Diverges. And why? Piece series or harmonic, however you choose to do it. So the given series. Now, at the point where I say the given series, I either decide which one's less writing. Is it this stuff or the given series? And whatever is less writing, that's what I do. 2n plus 1 over n plus 1 squared. It is, or diverges rather, also. They have to both behave the same. The harmonic diverges, so ours diverges. You follow? Okay, last one. 12. Oh, 4. 12 is okay. Okay. What'd you compare it to? 1 over n cubed. Great. Okay. Okay. Now, although finding the wrong limit value, say you would say the answer is 1/3 when it should have been 1/27, will that affect your conclusion? No, but will I mark off for you bad limit skills? Yes, I will. Okay, I can expect you to evaluate a limit law. What's the limit here? 1 over 1, 1 over 3, 1 over 27. 1 over 27. It's 1 over 27. Okay? Now that is finite, which is to say that I guess you could say that means the piece series here is 27 times as big. But the converge diverge the same way. Or their terms approach 27 as big. So you'd say because that limit of 127 is finite, not zero. Both converge or both diverge. I'm abbreviating. That is acceptable in the AP test, converge and diverge, although, if I were doing this for the president or for, well, not for the president, whatever, I would do a better job, okay? Sorry. If, say, because, 1 over n cubed, does it converge or diverge? My hero, maybe I would say, one converges. The given series, 1 over 2 plus 3n, it converges. Okay? So, with a comparison test. Do you feel like you can do it? I hope the answer is yes, because there's a whole ton of them in tonight's homework. Otherwise, you're going to have real hard tonight homework. Questions on... I have no idea what you guys want. What do you have? That's it? Oh, I made you turn in your homework yesterday. I didn't even grade it, so I should let you keep it. Oh, well. My bad. Just a little behind. Questions on set 132? Questions on 132?
23.
Did I hear 5 and 23?
23.
Did I hear 5?
Yeah.
I did hear 5? What was that?
There was a 2.
There was a 2 in there. 5, 23, and 2. Was 23 a question, though?
Yes.
It was us. Yeah, yes, yes. Right up. Okay, here we go. 5. 132, number 5. Inside sine and sine 2 theta. Ooh, good one. Okay, first of all, a gentle review. What's the max R in both cases? What's the max R? 1. Okay, so given that you have 5 rings, would it make sense to make these little baby pictures? No. The point of the picture is to help you, and it doesn't help you if it's microscopic. So, if this is the case, would you please change the scale for Pete's sake and call it something bigger so your picture's actually of some value? Sine of 2 theta, what kind of graph is it? A rose, lemniscate, a circle? It is a rose with how many petals? 4. Symmetry at the y-axis. You could get symmetry at the y-axis 2 ways. Is it this? Or is it this? It's that one, yeah. It's that better. Okay, so it's this one. It starts at 0. By the time it hits pi over 4, so doggone it, I don't know. The question is, this goes to loopy roses or not. Is it this? Or is it this? I don't know either. How are we going to answer that question? Let's look at a point. At pi over 6, what's sine of pi over 6? 1/2. At pi over 6, what's sine of 2 pi over 6? Root 3 over 2. So which is bigger at pi over 6? The sine of theta or the sine of 2 theta? Sine of 2 theta. So that tells me at this point here, that sine of, FERPA, sorry. At this point here, the sine of 2 theta is bigger. So it looks like that. The rose is outside. And the circle is inside. Now that makes sense to me because as we get closer to pi over 2, sine gets bigger. And this guy gets closer to pi over 2 quicker, so it'll get bigger faster. The rose will be outside, further out than the circle. Are we cool? All right, so then I feel like after that, I'm good. Okie dokie. I've got a good idea of the picture. Here we go. Number 4, 5. Inside both. So, if I draw spokes, inside both here is going to the circle. Up to that point where they meet. I'll call that back spoke region, region 1. But then, inside both means to the rows. So there are 2 regions times 2. We've got to do this with 2 integrals. Are you with me? Are you with me?
Yes.
So 2 times a half. Black region 1. How do I find it? I already pulled out my half and I'm already doubling, so just tell me the integral. That's 0 to, don't know. Maybe that's the question in trigonometry. Where does sine of theta equal sine of 2 theta? If you divide out sine and say 1 equals 2 of this. Okay. 2, yeah, this is a no-go. You'll need to get them to be the same argument, so use an identity. Right? Is it okay to, in math, is it okay to divide out a function? No, that's bad math. You don't do that, you just lost 0. So, instead, what is the way to solve this properly? Subtract and factor. So if you subtract and factor 2 sine of theta cosine of theta minus sine of theta is 0 equals sine of theta factored out, 2 cosine of theta minus 1 in. Sine of theta could be 0, and that's at 0, and pi and 2 pi and such. And cosine of theta could be 1/2. At what angles is cosine 1/2? Pi over 3. And this is where you don't trust your eyeballs. Okay, where else? Don't you dare look at that picture. Solve that trig for me, please. Actually, it wouldn't even matter. But where else is sine pi over 3? Or 1/2? 5 pi over 3. So that's going to coop people out that trust the picture too much, because 5 pi over 3 is here. And you think, what the heck? Something's going on. What's going on? Yeah, remember, you're not saying, oh, wait a second, there's no point. These things are made at totally different speeds. And at 5 pi over 3, the circle has gone around once and is almost ready to come around twice. That's 5 pi over 3 on the circle. Okay? And the rows has gone 1, boom, boom, boom. And there, by 5 pi over 3, it's there. So if you're thinking, wait a second, it doesn't look like 5 pi over 3 on the unit circle, it's not going to. You are oversimplifying. It doesn't work that way. It doesn't work that way. Okay? So, that said, that's why I've implored you forever to use symmetry. Because the first one point is easy. The points after you've gone around, things start to get complicated. So use symmetry. So if we go the region from 0 to pi over 3, then we don't even have to sweat that because we're doubling. I just wanted to make a point, don't trust your eyes. Am I talking sine of theta or sine of 2 theta in this black spoke region? Is it going to the circle or the rows? Circle, and what's the equation for that circle? Sine. Straight up theta. Squared d theta. Okay, that's region black. Region red. That also is now going to pick up at pi over 3. When will region red end? Ends when what goes to where? When which graph equals what r? When you say it again? When the rows equal 0. Beautiful. When the rows equal 0, and where does that happen? When 2 theta equals? Sine is equal to 0 at 0 and pi and 2 pi, so that's when theta equals pi over 2. Okay? And that's to the rows, so we use sine of 2 theta squared. Okay, you with me?
Can you, I don't know, can you shade the region that you just found with pi over 3, pi over 2?
Sure. It's the red region here, but it's this one.
Oh. Okay.
Okay? I didn't highlight that very well. All right. Questions? If you're not with me, say so. We can go over it again. Whatever it's
So why don't we double?
I did. That's what this is for. This too doubles. Okay? This, I put the whole thing in brackets, so I'm doubling both integers. Okay? Okay. 23?
Yes.
23? It's making me crazy. Okay, 23. There we go. Yeah. Yeah. So this goes to first step. What's a great first step? Separate, yeah. And it starts to look like an E. Yeah.
Oh.
So then you can go about it. I imagine this is probably headed for either e to the 4th or e to the 1/4. I can never remember which way it goes. But, after that, I would make a substitution. But if you can see it, I'm okay. Okay. 2. Question on 2. Parallel to the y-axis. This is rough. Parallel to the y-axis.
Yes.
Is isosceles right, hypotenuse in the base. So that means the right angle's up here. Right? Do you agree with the picture? And so one picture might look like this. Right angle. It's isosceles right, which means these are 45 degrees. Are we cool? Now before I go to my x's and y's, I need to get my geometry figured out. We have 2 approaches here we could do. Which did you try? Feels like this one's not so great here because I know angles, but I can find this side, but I don't know about these, so I don't think that one's well here. Let's go base height divided by 2. Let's go one further. What's the relationship between the base and the height? Geometrically. Anybody, whose question is this? Can I help you? I don't want to talk to myself. I've already done it. So because this is 45, 45, 90, isn't this also, this red one, also 45, 45, 90? So what does that apply about these sides? They're the same. That is to say that the height is equal to the half base. If I throw that in there, then the area is base over 2 times base over 2, or base squared over 4. That's not bad. So the area then is 1/4. Okay, now you just have to be careful with the base. What's the base of these triangles? The function or 2 functions? 2 functions. Remember, because it's a circle, it's not really a function at all. It's the square root of 1 minus x squared and the negative square root of 1 minus x squared. So it's really twice. Yeah. Why would I do what? Why would I do this? Because this whole thing is the same. I am finding. So why is this here? Is that what you're asking? Or? I did for the area. Oh, I might have made a mistake. So first of all, let's go back. Do you agree the triangle is base height divided by 2? The base is in the plane, so I'll be wanting to use the base. So I want to try and sub in for the height. Now, do you also agree that the height is 1/2 the base? So if I plug that in here, that's where I got this stayed the same. And instead of height, is right? Unless I made a mistake. Okay. I feel confident. So the X region is from -1 to 1. Okay. Okay. Let me know if you have questions.